After identifying the moments and shears, we can move to the design of the reinforcement of the deck. You are in bridge engineering. AASHTO has the LRFD procedure in the design of the deck. It starts from the identification of the bridge geometry to the calculation of the shears and moments, then the design of the reinforcements down until the limit state verification. Let's make a quick rundown of the steps. The first phase is the specification of the material and the identification of the geometry. For the deck or the slab, we have to take note of the effective depth, which is taken as the total slab thickness less the clear cover, then half of the reinforcing bar diameter. We also have to determine the modular ratio, which we have identified in the distribution factor before. When using the elasticity modulus, remember that E for steel is 200,000 megapascal, and the elasticity modulus of concrete is solved from 4,700 by the root of F prime C. In order to take the depth, we need the clear cover, and the AASHTO provided the cover for unprotected reinforcing steel in millimeters. These values are specified according to the location, like the top deck cover or the bottom or soffit cover. The second phase includes the determination of loads using the strip method, where the strip is taken perpendicular to the traffic. The most basic loadings for the discussion are the dead loads, both from the component and the wearing coat. Then the live load computed from the design truck or the design tandem and the design lane. After which, we convert the loads into shears and moments by using the AASHTO tables of factors for the different limit states for strength, service, fatigue, and extreme events. After learning the shear and moment for each girder, we move further by designing the deck reinforcement. Then we check flexure. First is to compute for the required steel area, where we use the computed ultimate moment from the strength limit state and compare this with phi by the nominal moment. The nominal moment being solved from A sub s multiplied by F sub y times the depth less half of A. We already know Fy and the depth, and we can compute the block depth A from As times Fy over 0.85 of F prime C times B, where B is the strip width of 1 meter. To check flexure, the minimum reinforcement A sub s should be sufficient to resist either 1.2 of the cracking moment or 1.33 of the ultimate strength moment. If the flexure is okay, we then continue with crack control. This is for the purpose of checking that the bar spacing is enough to prevent cracks. Another new parameter is introduced at this point, the F sub SS, or the reinforcement stress, which is computed from the elastic crack section. The equation is the moment with the service factors all over A sub S with J and D. AS is the area of the tension reinforcement which was solved in the previous phase. This is the effective depth solved from the first phase. J is the internal lever arm, which ranges from 0.87 to 0.9 for a typical 200 mm bridge deck. So incorporating the range, we can use the equation of the service moment upon A sub S times 0.88 times D. 0.88 is the most common constant used for J. To control cracking, we then have to determine the maximum spacing, which is taken as 123,000 gamma sub E upon beta sub S times F sub double S, then deduct twice of D sub C. D sub C is the distance from the tension phase to the center of the bar, and gamma E is the exposure factor, which is simplified into two constants. Class 1 exposure uses gamma E of 1, and this is used for standard conditions. For severe conditions, we use gamma sub E as 0.75. Beta S is the ratio accounting for the difference in strain between the steel reinforcement level and the extreme tension of the concrete face. This is computed as 1 plus D sub C over 0.7 of H less D sub C. D sub C is the same as notated earlier, and H is the total depth of the slab. Phase 5 is for the fatigue limit state, where we design and check the longitudinal bars of the deck. The bottom longitudinal bars are taken as a percentage of the main bottom steel. The percentage should be not more than 67% of the transverse main reinforcement, which is 3,840 upon root of S. The top longitudinal reinforcement should be enough to counter temperature and shrinkage. The temperature and shrinkage area should be equal to or more than 0.75 of the gross area of concrete upon Fy.